Here are the solutions. In the first exercise, slider B has a simple harmonic motion that can be written as A times cosine of theta plus B. Then in order to find the velocity of point B, we need the first time derivative of the position, which becomes minus A times omega, the angular speed of the crank, times sine of theta. And finally, for the acceleration, we need the second time derivative, which is equal to minus A times omega squared times cosine of theta. Notice that the angular speed omega is constant and has no time derivative. So this way, by twice time derivation, we could find the acceleration of slider B in terms of the rotation angle and the constant angular speed of the crank. In the second exercise, we have a Scotch-Yoke mechanism with a curved yoke. We can write the position of point B as A times cosine of theta plus B times cosine of phi. Since we need this position as a function of theta, we need to find the angle phi in terms of theta. As you see in this illustration, A times sine of theta and B times sine of phi are both representing the same thing. From there, we can write the sine of phi as a function of theta. But we need the cosine of phi, which can be computed as the square root of 1 minus the sine squared of phi. And substituting this sine of phi, we will have it in terms of sine of theta. Finally, substituting the cosine of phi in the expression, we will have the position of point B as a function of theta. And by putting B inside the square root, we can simplify it a bit.